Hello everybody, and welcome back to another quiz tutorial. So in this tutorial, we're going to be covering quiz number 13, which is deformation and displacement gradients. Now, when you guys see these, I guarantee you guys won't like them. They're going to look really ugly, like really ugly. But don't worry, it's actually really easy, and this is good news because these deformation and displacement gradients, these are the first step into what I like to call kind of true continuum mechanics. Thus far, basically all we've done is cover the basics. And what do I mean by the basics? Well, kind of the prerequisites. Well, we covered the orthonormal basis sets. We covered some linear algebra, make sure that all the skills are up to par. But now we're actually getting into the good stuff, which is actual deformation, displacements, stuff like that. And what we learned here is kind of the first major step, because with these deformation and displacement gradients, we can start deriving things that have to do with stresses and strains. And that's kind of the goal of this course. You guys are civil engineers. The goal of this course is to say, okay, if I have a structure, I want to analyze the stresses and the strains in the structure. How do I do that? Well, we start here, which is deformation and displacement gradients. So I know that you guys are so excited to get into this. I am too. So let's jump into the theory. So before we get into the equations, let's just take a step back and discuss what exactly deformation really is. So we're first going to see how this relates to the earlier topics we've already discovered. So let's say that we have a little space guy here. I know some of you guys will know who this is. I know some of you guys will not. So we're just going to call it little space guy. And he has a point on him. So that little black mark, that's what we're interested in. His position right now, that little black mark. Well, the first thing that we have to realize is that if we don't define a coordinate system, this is all meaningless. He's just a point on your screen, but you have no idea where that point is in space. So when we're considering deformation, it's very important to discuss, okay, well, where is our coordinate system? Where are our basis vectors? So now you guys are saying, oh, okay, Clayton, this is why we spent so much time talking about orthonormal basis and orthogonal matrices and all that sort of stuff, because it's going to start defining our coordinate system when we start talking about stress and strain. Because if we define a coordinate system such as this, we can define a position for this guy. And what this big X is the position with respect to the axis. So it's initial position. So as you guys will see here, and this is what I find confuses students the most about deformation and displacement, you're going to see three different symbols. You're going to see a big X, which is its original position. So that big X right there, that's a coordinate point. From here, I can say that that guy's coordinate position is, let's say, 1, 3, -2. Well, that's going to be my big X. Now, the second two that you're going to see is going to be a little x and a little u. And the problem is that a lot of students will not really understand, okay, which one is which and what exactly do they mean? So let's look at our little guy here and say, okay, he's having fun. He's having a great time. Oh, wait a second. This guy's an imposter. Well, what do we do with imposters? We kick him out. So let's say that we throw him out so he displaces, and at the same time we stretch him a bit, stuff like that, so he undergoes some sort of deformation. Now the question becomes, okay, well, he had his original coordinate points over at x, big X, and now he's moved somewhere. Well, how do we define where exactly he moved, and what's the relationship? Well, the first way is to say, okay, well, if I know where he is at the start, I can find his displacement. So that u right there, that's his displacement from one point to another point. So that u there, if we were ever given u, we call those displacement functions. So it takes its current point and it maps it to its next point, or its, I guess its original point, and it maps it to its current point. Now we can say, okay, well, hold on a second. I'm doing everything with respect to this basis system. So what we can do is we can define kind of a second type, which is called a position function. So this position function x, this is what you're typically going to be given. And this relates where the guy is with respect to the coordinate system. So again, that displacement function u, that relates the guy to his original position, where x relates it to the coordinate system. And if we look at this and kind of remember Eng 130, you go, oh, I remember in Eng 130, this kind of looks like a parallelogram. Well, it is, because it follows the rules of vector addition. So from here, we can also see that that small x, the position function, is equal to big X plus u, which makes sense. It's basically saying that our new position is equal to the original position plus the displacement we had on that object. So now let's start talking about the actual gradients. So there's going to be two gradients, and they sound so similar. We have the deformation gradient and the displacement gradient. So I guarantee students are going to start mixing them up. But let's start with the deformation gradient. And this is going to be the more important of the two, the one that you guys will use more frequently. So if we're given a position function x, we can find the deformation gradient. So if we have x is equal to x1, x2, and x3, we can find this deformation gradient f. And as we can see here, this is going to be a tensor, a second order tensor, or if you guys are more interested, a 3x3 matrix. And if we look at what's inside that matrix, well, we're going to pee our pants a little bit because that looks pretty crazy. You're thinking, oh, Clayton, oh my God, what have I got into? What am I going to do? But it's actually very simple. All we're going to do is take our x1 in our position vector, or sorry, our position function, and we're going to take 3 partial derivatives. And as you guys will see, Dr. Sammer is very kind. We're not going to give you any crazy derivatives. And as you guys will see, the partial derivatives are actually very, very simple to handle. So instead of me trying to explain how easy it is, I'm just going to show you guys the examples in the quiz, and you guys are going to, oh, Clayton, this piece of cake. So the second gradient we can look at is called the displacement gradient, which is nabla u. So let's say that instead of a position function, they give us a displacement function, which is called u. Well, from that we can find the displacement gradient, which we call nabla u. And if we look at the formulations, yes, they look gross, just like before. But if we actually look at the components, the only difference between nabla u and our deformation gradient f is that instead of lowercase x, we have the u instead. So that's all we're doing is we're swapping lowercase x with u, but the formulation's again the same. And again, please don't just trust me that it's easy. Wait till we go through the example and you guys will actually see for yourselves. Yes, this calculation is a lot easier than it looks. I know when I first saw this, I'm like, oh God, this course, oh, it's that kind of course. That's what people said to each other. Oh, it's going to be that kind of course. But it's not going to be that kind of course. It's actually not too bad at all. So now we have to ask ourselves, well, we remember that lowercase x is equal to big X plus u. And that makes sense. From the picture, we saw that. We were, okay, this makes sense. So are the gradients related to each other? And the answer is yes. So if I have my nabla u, let's say, all I have to do in order to find our deformation gradient f is I just add the identity matrix. And since we're dealing with 3x3 matrices, the identity matrix will just be the diagonal matrix 1, 1, 1. And you guys should know identity matrices from before. It's very simple. Or on the other hand, let's say that we know the deformation gradient f. Well, in order to find nabla u, all I have to go is f minus I. So I highlighted these with a nice box because these are going to be very important because it allows us to switch from one of the gradients to the other very, very quickly. And you guys will need this not only for the quiz, but for your assignment as well. So the last thing we're going to talk about is some of the deformation characteristics. So again, we have f and we have our nabla u. We can say, okay, well, what properties can these tell us? So the main thing we're going to do is we're going to look at the deformation gradient f. And more specifically, we're going to look at the determinant of f. And you're going to say, well, Clayton, why exactly are we looking at the determinant of f? What exactly is the determinant of f? Well, the determinant of f is actually the ratio of the volume after deformation compared to its initial volume. So from this, we can conclude a bunch of facts. So the first one, we can actually say, is the deformation physically possible? Well, if the determinant of f is greater than 0, this means that the deformation is, yes, physically possible. And the reason why is there actually is some change in the volume ratio. Now, if the deformation was less than or equal to 0, this means that it's physically impossible. Well, what exactly does this mean, Clayton? Well, in order to get the determinant of f less than 0, it means that our object after deformation has a negative volume or a volume of 0. And because we push things and we deform them, well, very rarely do you see us push something and then it just disappears. So because of that, we can conclude that yes, if we have a negative determinant or it's equal to 0, the deformation itself is actually physically impossible. And the second thing we can say is, okay, well, is the deformation an expansion of the object? So is it getting pulled apart? Is it contracted? So is it being compressed? Or does the volume of it stay the same? And again, we look at the determinant. So if the determinant is greater than 1, this means that our new volume is greater than our initial volume. It means that there's expansion. If our determinant is less than 1, it means that there's a contraction because, again, our ratio of volumes is less than 1. It means our new volume is less than the original volume. Or finally, our determinant of f is equal to 1. So this means that our volume after deformation is exactly the same as our volume before deformation. And for those of you who want to take this a step further into kind of higher level courses, this determinant of f actually has a special name, and it's called the Jacobian. And it's very important in finite element analysis, as you guys will see. So the final one I want to talk about is this question here. Is the deformation homogeneous? Or in what I put in simpler terms, because let's be honest, if I ask, is the deformation homogeneous, everyone's, well, what the hell does that mean? Well, it means does every point in the object experience the same deformation? Well, how do we check that? We look at the determinants, and there's going to be two cases, and you guys will see this in the quiz. The first one is the determinant of f is equal to a constant. So if I have my f matrix or my tensor, and I find the determinant and it's just equal to a number, let's say 6, then yes, it's homogeneous. But what you guys will find out is not every case where our determinant is equal just to a single number. For instance, we'll have the case in the quiz where our determinant of f is actually a function of x1, x2, and x3. And what does this mean? Well, it means that the volume is changing dependent on the position of where the object is. And if this is the case, this means that it's non-homogeneous. So I know that this theory lasted a little bit longer than before, and which kind of sucks because that implies that it's more complicated, but it's actually, again, really simple. And when we go through the quiz, you guys are actually going, oh, this is a piece of cake. It looks like ass, but it's a piece of cake. So instead of me rambling on about it, let's just jump into the quiz so I can show you how easy this actually is. All right, so the quiz is nice in that it's just basically the same question repeated in 4 different scenarios. So it says for each position function, determine the deformation gradient, and I'm going to actually write this down. So the deformation gradient right here, this is going to be f. It wants the displacement gradient, which is nabla u. And then finally, it asks us 2 different questions. The first one is the deformation possible? And is the deformation an expansion, contraction, or volume preservation? So we know that for these 2 right here, as we talked about in the theory, these are going to be related to the determinant of f. So I'm just going to put determinant of f. I kind of squeezed it in there. But yeah, so if we look at this, it's basically going to be 3 different things we're going to have to find. First one's going to be our deformation gradient f. And then from there, we can find the determinant to answer questions 3 and 4. And then after that, we can find the displacement gradient, which is nabla u. We're going to come down here, and this is going to be our first one. And we're given x is equal to x1, x2, and x3, where x1, x2, and x3 are these nice equations. So just to show you guys what I mean by x1, x2, x3, this first column here, this first row here, this would be x1, and then we have x2, and then we have x3. So I'm going to erase the highlighting, and we're going to come down here and say, okay, well, if I want f, so here's going to be kind of the big thing. If I want f, we know it's going to be a tensor. It's going to be a big-ass tensor. And I'm not going to write down the formulas for you guys because it's kind of tedious, very tedious, and I don't want my videos to be tedious. I'd rather ramble on about something off topic than make tedious matrices. But what we remember is that the rows of f, of this tensor, are going to be the partial derivatives of x1 with respect to big X1, big X2, and big X3. So this first row here of f is going to be the partial derivatives of x1. So I'm going to highlight x1 here. And I'm just going to go through and I'm going to take the partial derivatives with respect to each one of the big x's. So the first one is going to be partial x1, where x1's the small one, divided by the, I'm mixing this all up completely. I'm going to take the partial derivative of small x1 with respect to big X. If I come down here and I say, okay, well, the first thing that I got here is I got 0.8 x1. Well, the partial derivative of that with respect to x1 is just going to be 0.8. So you guys can see how this is going to be easy if we're only given linear or quadratic functions. And if you guys remember, it's basically the derivative of x is equal to 1, and that's how I got the 0.8. I go to the second component and say, okay, well, what's the partial derivative of 0.2 x2 with respect to x1? Well, I realize I don't have any x1s in there. So this one over here, for the second case, this will just be, this will be plus 0. And then I move on to the third term, which is right here, which is the partial derivative of 0.01 x3 with respect to x1. Well, again, I don't have x1 here, so this would actually just be 0. So my first term in that deformation gradient f is actually just going to be 0.8. So I'm just going to leave this as 0.8. And then I come down and say, okay, well, now I have to go through all 3 terms again. except instead of differentiating to big X1, I'm differentiating with respect to X2. So if I go to the first term, I'm taking the partial derivative, and I'll highlight here. I'm taking the partial derivative of 0.8 X1 with respect to X2. Well, that's going to be 0. So I'm not going to include anything. I move on to my second term, and I say, okay, I'm going to take the partial derivative of 0.2 X2 with respect to X2 and say, okay, well, I have an X2 and I'm differentiating with respect to X2. So we can see that this one right here is going to actually just be 0.2 because again, the derivative of X is equal to 1. And then my last component, well, I have X3, but I'm differentiating with respect to X2. So that one will also be 0. So then finally I say, okay, well, I have the first two terms. I'm going to move on to the last term, which of course is differentiating with respect to partial X3. So for partial X3, I'm coming down and say, okay, well, the first term has X1, therefore it's going to be 0. The second term has X2. Again, I'm differentiating with respect to X3, so that's going to be 0. But then my final term has an X3. So from there, I say, okay, well, I'm going to take the partial derivative of 0.01 X3 with respect to X3. The derivative of X is just equal to 1. So in the end here, I'm going to get 0.01. So I'm just going to erase this now. And this is going to be the first row of my deformation gradient f. And after that, I say, okay, well, I'm done with that equation x1. I'm going to move into small x2. And this is it right here. And as you guys can see, I'm not going to have to really go through these anymore. If I realize that, hey, if I'm differentiating with respect to x1, then I only care about the terms that have an x1. So now in the second row, remember, I'm differentiating this equation here, small x2, with respect to x1, x2, and x3. So with respect to x1, I'm just going to say, okay, well, this is the only term there that has an x1. Therefore, 0.01 x1 differentiated with respect to x1, well, this is going to be 0.01. Say, okay, how about x is equal, differentiating with respect to x2. Well, I can say, okay, well, now this is my only term with respect to x2, is that 0.9 x2. And if I take the differential of that, I get 0.9. And then I move on to x3. Well, none of these have an x3, so at the end, it's just going to be 0. So again, I'm probably butchering this because I'm mixing up the x's and stuff like this, but basically, all we're going to look for when we're differentiating with respect to something is the components with respect to that. And the best example is if we look at the last one here, which is small x3, and I'll highlight small x3 and I'll erase the highlighting around x2. If I were to look at this, I can see that there's no x1 or x2 within this equation. So therefore, the derivatives with respect to x1 and x2 are going to be 0. And then finally, I take the derivative with respect to x3. Well, that's just going to be 1.4. So I'm going to come down here, go 1.4, and this is the answer. So as you guys can see, instead of doing all this work and all this tongue twisting that I've been doing, it's very easy just to look at this and get these values. If I were to look at 0.8 x1, well, I remember if I differentiate that with respect to x1, I get 0.8. And I can just go through each one of these equations and figure out what they're going to be. Now, here's a little trick. Well, not a little trick, a little tip. It's always not just going to be the coefficient. So if we look at the small x1 above, this equation that I'm highlighting here, you notice how the coefficients were 0.8, 0.2, and 0.01. And if I look at my first row of f, and I have 0.8, 0.2, and 0.01, it's not just as simple as taking those coefficients, because some of the position functions can be a function of x1, let's say, squared. And we know if we take the partial derivative of this, it's not just going to be the coefficient, it's going to be 2x1. So there are cases where inside of our deformation gradient f, we're still going to have the variables x1, x2, and x3. But for this one, since all these terms were linear, so none of them are squared or cubed or anything like that, we see that our f tensor is actually pretty constant, just full of a bunch of constant numbers. And remember that we said that if we know the determinant of f, which I'm just going to switch colors, if we know the determinant of f, we can find out a bunch of other stuff. So the determinant of f in this case, you guys know how to do, you guys are experts at, we find is 1.0052. So again, I didn't show you guys how I got that, but you guys know how to take a determinant of a 3x3 matrix. So from here, we can conclude a bunch of things. The first one is this determinant is greater than 0. So therefore, this is physically possible. So I'm just going to write possible right there. And what this means is there was a change in volume in that the new volume is not negative and it's not zero. So therefore, this is a physically possible deformation. And the second thing we can see is this deformation is greater than 1. So therefore, this has to do with an expansion. So I'm just going to write expansion. And again, this is because the determinant is greater than 1, which means that the volume of our deformed shape is greater than our initial shape. So this is why it has to do with expansion. And if we remember, the final thing the question wants us to do is it wants us to determine that nabla u. So this is where we're going to have to use our properties, and we say, okay, well, I remember that nabla u is actually equal to F minus the identity matrix I. So all I have to do is take all of those diagonal components of F and subtract 1. So kind of the first hint I'm going to give you guys, all the non-diagonal components, and what you're saying, Clayton, what do you mean by that? I mean, these components that I'm highlighting here, they're all going to stay the exact same. So when I come down here, I can actually start filling this out with the non-diagonal components and saying, okay, well, I know that this is going to be 0.2, 0.01, and we have 0 here. And then on the other side, we have 0.01, 0, and 0. Now, what do we do with those diagonal components? Well, we're subtracting the identity matrix. And if you guys remember, the identity matrix is just a diagonal matrix where the diagonal entries are 1, 1, 1 for 3 by 3. So all we're going to do is we're going to take these values, and I'll highlight them in a different color. Let's go green. We're going to take each one of these diagonal components, and we're going to subtract 1 from each one of those. So if we go 0.8 minus 1, well, we get negative 0.2. If we go 0.9 minus 1, we get negative 0.1. And finally, if we go 1.4 minus 1, we're left with just 0.4. So if we have our deformation gradient f, it's very easy to determine our displacement gradient nabla u. We just subtract 1 from all the diagonal components, and the rest stays the exact same. So this is the question. It took a long time because I kept getting my tongue twisted on all the partial derivatives, but as you guys can see, it's actually pretty simple to do. Now I'm going to try to do a lot better job when we come down here to part B, where it says, okay, our position function now is equal to qx, where q is actually equal to, oh, wait a second, that's a rotation matrix. You guys have seen this before. Nice and simple. So for those of you guys who are wondering, if you guys don't exactly know what's going to happen right away, what I suggest is just sub x into q to find what our position actually is. So if I were to go x is equal to xq, well, then all I'm doing is I'm taking that rotation matrix, which I'm going to just go cosine of theta, sine of theta, 0, 0, 1, 0, 0. I know you guys get so bored of watching me just write this all the time. Times cosine of theta. And then what we're going to do is we're going to multiply this by x, which in this case is just going to be x1, x2, x3. So right here, we have x1, x2, and x3. So this is what it means by x is equal to q of x. It means that it's going to be equal to this. And as we can see, if we were to actually do these calculations, what we'll see is that x is going to be equal to, and I'm just going to write it out again. It's going to be equal to cosine theta of x1 multiplied by sine theta, or not multiplied by, the next component would be sine theta, x2, and then 0, x3. Well, 0, x3, that's just going to be 0. I come down, I do the exact same thing. I'm going to have negative sine of theta x1 times cosine of theta x2. And this will be 0, and 0, 0, and then the last entry will be 1 times x3. Well, in this case, this will just be x3. So in case you guys are wondering what the position function actually is, we can just do this simple multiplication to figure it out. And then from here, we can take the partial derivatives of each one to find f. So if I go down here and I go f is equal to, I'm going to come down here, just draw the line. I'm going to say, all right, well, what is the derivative of cosine of theta x1 with respect to x1? Well, that's just going to be cosine of theta. What's the partial derivative of sine theta x2 with respect to x2? Well, that's just going to be sine of theta. What's the partial derivative of 0? Well, you guys already know that's just going to be 0. And I'll fill in the rest of the 0 entries because you guys are smarter than that. And I guess there'd be one here. We go to the second row. What's the partial derivative of sine theta x1 with respect to x1? Well, that's just going to be negative sine theta. And what's the partial derivative of cosine theta x2 with respect to x2? That's just going to be cosine theta. And then finally, at the very bottom corner, what's the partial derivative of x3 with respect to x3? That's just going to be equal to 1. So we come down here and we say, okay, well, now we have our f, and we can do stuff like the determinant to figure out more information. But if we look here, we say, oh, wait, that looks familiar. And if we scroll up here, we can see that our f, our deformation gradient, is actually equal to q. So this right here is equal to q. So for those of you stuck on the quiz saying, why does it have one box for all the components of f? Well, that's because f is just equal to q in this case. And we know that q has a determinant of 1. So from q, and this is what we learned before, and this is why we learned all this stuff before, determinant of f is going to be equal to the determinant of q, which is equal to 1. And remember, since this is equal to 1, we can conclude a couple things. One is that it's greater than 0, therefore this is definitely possible. And the second one is it's equal to 1. And I guess I don't need to put equal to 1 again. And if something is equal to 1, it means that there's volume preservation. So basically the change in volume is 0. Volume preservation. So again, this means that the volume after deformation is the same as the initial before deformation. And from there, we can conclude something very special. This right here is a rigid body motion. So basically, the object's not deforming, it's just being displaced or rotated. And that makes sense because if we look up here, well, our transformation was the rotation matrix. We know that all we're doing to this object is just rotating it. We're not deforming it, stretching it, anything like that. We're just rotating it. And that's why we get the determinant is equal to 1, which indicates volume preservation. And of course, we're rotating an object. You guys can easily see in real life that this is definitely something that's possible to do. So now we're going to come down here and say, okay, we're given the same scenario where x is equal to mx, where m is equal to that matrix. And I'm not going to go through it because it's a little bit lengthy, but what you guys will see again is f is actually equal to m in this case. So I come down here and I'm going to say that my f, well, this is going to be equal to, let's come down here, 1.1, 0, 0, 0, 0.9, 0, 0, 0, and 0.8. Now, from here, we can find the determinant just like we did before. So if we were to go to the determinant, and I don't know why I switched colors. If we were to go to the determinant of f in this case, what we get is that the determinant is equal to 0.792. And the two things we conclude are this. One is this is greater than 0. Therefore, this is actually possible motion, possible deformation. And the second thing is this is less than 1. So therefore, this is actually a contraction. Which means that the volume after the deformation is less than the volume before the deformation. So that's kind of nice. Determinant of f, it tells us a lot of things. That's why it's very important later on when we start talking about finite element and Jacobians and stuff like that. So I'd come down here and say, okay, well, the last thing I need to do is nabla u, which is going to be equal to f minus I. So again, in order to find this, all we need to do is take those diagonal components and just subtract 1. So even though the non-diagonal components are 0, so all of these are 0 already, so we don't really have to do anything. But remember, these ones don't change between f and nabla m. So if I wanted to, I can just right away go 0, 0, 0, 0, 0, 0. I come up here and say, okay, and all I'm going to do to my diagonals, which I'll highlight right here, is I'm just going to subtract 1 from each one of those. So we got 1.1 minus 1, well, we're left with 0.1. We got 0.9 minus 1, we're left with negative 0.1. And finally, we have 0.8 minus 1, we're left with negative 0.2. 2. So as you guys can see, it's actually pretty easy. I talked to you guys about how the math looks gross, and yes, it does look gross, but the process itself is very easy, so hopefully you guys are starting to see, yes, this is a piece of cake. Now, what I hope you guys don't do before is watch question A or maybe question B and say, oh, this is too easy, I don't need to watch the rest of the video. Because we're going to get into something very special here. And if we look at this function, it looks just like before. We're given x1, x2, x3, blah, 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 blah. But if we look here, we have some components that are squared. And these squared things will change something. So I'm just going to erase this, and I'm going to say, okay, well, let's pretend we didn't notice the square. And let's go through here and say, all right, we have f is going to be equal to, and I'm just going to draw the line. So again, I'm just going to go through x1, and I'll put these on the side, x1, x2, and x3. And what I'm doing is I'm just going to go through each one of these and take their derivatives with respect to x1, big x2, and big x3. So if I were to look at the first equation, which I guess I'll highlight so you guys know exactly what I'm doing, and I were to take this with respect to partial x1, well, I'm going to get 0.8. And then usually this would be it. But if we look, there's a second component that contains x1 right there. So the partial derivative of 0.01 x1 squared is going to be plus 0.02 x1. Sound good? This is where the tricks start happening. So hopefully you guys see where that came from. So where I got the 0.8, I just differentiated this term right here. Where did I get the 0.02 x1? Well, I differentiated this second term right there. So that's my first component in my matrix F. That's not two components, that's one single component. And I'll put brackets around it so you guys can really tell that's a single component. Now, if I do the partial differential of this last term, with respect to x1, it's equal to 0, so that's why I'm not even including it. So I'll erase these again. Now I move on and say, all right, now I'm doing a partial differential of x1 with respect to big X2. Well, the first two terms contain x1, so they're going to be 0. But the second term contains an x2, so if I take the partial differential of this term right here with respect to x2, I get 0.04 x2. So notice how in our deformation gradient f, we have x1 and x2 in there. It's not just constant numbers anymore. And then finally, I can finish this off by taking the differential with respect to big X3, but there is no big X3, so in this last case, this will be 0. So what I'm going to do is I'm going to come down to small x2 now and take my three derivatives. So if I look, there's only one term in this one that contains x1, so I'm just going to differentiate that, which is 0.01. And I say, okay, great. Is there any x2s here? Oh, I have one term that contains an x2, so I'm going to do the partial differential of that. I get 0.9. And finally, is there any terms that contain an x3? Oh yes, this last term contains an x3, so I'm going to differentiate that. And what I get is 0.02 x3. So just like that. Come down here and say, all right, well now I'm going to do my final one for the bottom one, which is going to be small x3. First one, do I have any big x1s? I don't. Therefore, this will be 0. Do I have any big x2s? Oh, I don't again. Therefore, this will be 0. And finally, do I have any x3s? Oh, yes, I do. I have one right here. So I take the partial differential of that, and I get 1.4. So I'm just going to close up this bracket really quick. Something like this. So this is going to be our deformation gradient f. And again, this one's special now because inside of it, we have x1, x2, and x3. It's not just a function of constant numbers. It's a function of x1, x2, and x3. So if I were to take the determinant of this now, I was about to say derivative. I'm so used to saying derivative now. If I were to go the determinant of f, we know that this is going to be 0.8 plus 0.02 x1 multiplied by 0.9 times 1.4. And then this is going to be minus 0.04 x2 multiplied by 0.01 times 1.4. So what I'm going to do down here, because that's just a bit long, is I'm just going to expand it out into one nice equation. I get the determinant of f, which is called the Jacobian. So a little fun fact, I'll just put this as j, because it's called the Jacobian. This is equal to 1.008 plus 0.0252 x1, and then minus 0.000, so 3 zeros, ooh, quite lengthy, 56 x2. So now we're going to have to kind of ask ourselves some questions. Is before we take that determinant and we compare it, is it greater or equal to the 0? And then is it greater or equal to 1? Greater than, less than, or equal to 1. But now we don't know, because depending on what our values of x1 and x2 is, it'll change. Sometimes it will be less than 1, sometimes it'll be greater than 1, sometimes it will be even less than 0. So therefore, this kind of deformation is called, and I'll switch colors here to really highlight it, this right here is non-homogeneous. So non-homogeneous. E-N. I'm probably spelling this wrong, but that's okay. I'm a civil engineer. I'm not an English major. All right, so this is called non-homogeneous because depending on what our x1, x2, and x3 is, our determinant is actually going to change. So if the question did ask us for things like volume preservation, is it contraction, is it expanding, is it possible? Well, we're actually going to need a coordinate point to substitute into this formula so we can actually have a number. Because in this current case, it's non-homogeneous because it's dependent on those points. So last part of this, and wow, this is really getting into a really long quiz, and I apologize for this, guys. It's just something that's very important to know. Oops, I can't even do it right now. So nabla u is equal to f minus I. So again, all we're going to do is subtract 1 from all the diagonal components. So I'll just start my square brackets. I come up here, and I have 0.8 plus 0.02 x1. Well, if I subtract 1 from that, that 0.8 will turn into negative 0.2. So down here, I'm going to go 0.02 x1 minus 0.2. Because all I did was subtract 1 from this term right here. Now I'm going to go to the next diagonal term, which is 0.9. That's an easy one. 0.9 minus 1. I get negative 0.1. Look at my next diagonal term right here, the 1.4. Well, again, that's easy. I just go 1.4 minus 1. So I come down here. That's just going to be 0.4. And remember that all the non-diagonal terms, so I can't really highlight. I'll highlight in this color. All these non-diagonal terms that I'm highlighting in green, they just stay the exact same. So on the one side, I got 0.1, 0.01, 0, and 0. And on the other side, I got 0.04 x2, 0.04 x2, and 0, and 0.0 something, 0.2 x3. So I'm just going to finish this here. And we're good to go. So that concludes the quiz. One last little note that I want to leave you guys on is don't assume that just because there's a squared sign in here that things are non-homogeneous. Let's say that I didn't have a squared sign on x1 or x2. I'm scared that a lot of students will say, okay, well, x3 is squared, therefore this is going to be non-homogeneous. However, if we look at the determinant equation right here, x3 doesn't appear anywhere. So this would still be homogeneous even though x3 is squared. So again, just the final note, just because there's a squared sign, that doesn't mean you can tell if it's homogeneous or non-homogeneous, something like that. So just please keep that in mind. So that concludes the quiz. Again, yes, this was a beefy one. Deformation and displacement gradients are very important. As you guys will see, they're going to kind of form the base steps that we're going to use to solve our strain and stress matrices. So thank you guys so much for listening. If you guys made it to the end of this video, I really appreciate it. I will see you guys in quiz number 14.